Okay, we're going to continue with 14.4, and we left off with this function, and we were going to look at the equation of the tangent plane at this particular point. So first off, let's evaluate this function, f of ln of 3, comma 1. This is equal to e to the ln of 3, which is 3. And now we need to compute partial derivatives because our equation, recall that the equation of the tangent plane here is f of x0, y0 plus the partial with respect to x at x0, y0, x minus x0 plus the partial with respect to y at x0, y0 times y minus y0. So we need the partial derivatives of f with respect to x and y. So let's take partial of f with respect to x. What is that? Well, it's the derivative of the first term, y squared, with respect to x, which is 0. So 0 times e to the xy, plus y squared times the partial of e to the xy, so d by dx of e to the xy. So this is equal to y squared times e to the xy times chain rule, the partial with respect to x of xy, and that equals, we get another y out because y is constant, so we get y cubed e to the xy. So this is our fx. Our fy, well, we take partial of y squared, we get 2y and then e to the xy, plus y squared times the partial derivative with respect to y of e to the xy, which is 2y e to the xy, plus, and here when you take the partial derivative with respect to y of e to the xy, we get y squared e to the xy again, and then we take the derivative of the exponent with respect to y, we get an additional x out. So this is the derivative of f with respect to x and with respect to y. And now we need to plug in, so we plug in x equals ln of 3 and y equals 1. So for fx, we get we get e to the ln of 3 again, which is 3. For fy, we get 2 e to the ln of 3 plus ln of 3 times e to the ln of 3. So this is 2 times 3 is 6 here, plus 3 ln of 3. Okay, and so what's going to happen here is we're going to get the following equation of the tangent plane. So z is equal to, recall that f of xy, f of ln of 3 comma 1 was 3. So this was f of xy. So we have z is equal to 3 plus 3 times x minus, and x naught was the ln of 3, plus, and then fy here is 6 plus 3 ln of 3 times y minus 1. And so we can simplify this a bit. So we get z is equal to 3 plus 3x minus 3 ln of 3 plus 6 plus, let me make this the ln of 327, y minus 6 and minus 3 ln of 3. Okay, so we have the following. We can merge, so this 3 and this 6, so we get z is equal to minus 3. And then we can merge this minus 3 ln of 3 and this minus 3 ln of 3 to get a minus 6 ln of 3 plus 3x plus the quantity 6 plus the ln of 27 y. And that is our final answer here. Okay, we're going to just do one little more type of problem, which is linear approximations. So just like in one variable, so recall that if you have some type of function here, and you have the equation of a tangent line, so we have a tangent line somewhere here, so this is some x0, y0. If you want to find f of, so this is, there's going to be some, so here's x0, here's x1 that's pretty close by. F of x1 is pretty close to this point. What is this point? This is the linear approximation at x1, right? It's the equation of the tangent line where L of x is f of x naught plus f prime of x naught, x minus x naught. So instead of plugging the point nearby, which is x1, into the function itself, which depending on the function, it can be difficult to compute directly, we can approximate it by plugging it into the equation of the tangent line. So L of x1 is approximately f of x1. And the same thing holds true in multiple variables. So we have, say some surface here going like this, and we have a tangent plane at some x naught, y naught, that's lying just above it, or tangent to it, and we take another point, so here this corresponds to the base point x0, y0. If we take some point nearby in the domain, let's call that x1, y1, well, we have two options now. We can get the exact value, which is f of x1, y1, or we can take the equation of the tangent plane, and let's call it L of xy. So remember, L of xy here is f of x0, y0 plus fx at x0, y0 times x minus x naught plus fy times y minus y naught. So instead of taking the function f and directly, or taking the x1, y1 and plugging in directly into f, we can realize that, so f of x, or this red point here is L of x1, y1. So L of x1, y1 is approximately f of x1, y1. So let's go back to an example that we did a little earlier, where we had the surface 8 minus x squared minus y squared, and we were at the point 0, 2. And we saw that the equation of the tangent plane, and I'm going to use an L of xy just to use the same terminology. This was, what we ended up with was 8 minus 4y, where, or sorry, so it's 12. Because fx was 0 at this point, and fy was negative 4 at this point. And notice that this L of 0, 2 is 4, which is equal to f of 0, 2. So this is the linear approximation, the equation of the tangent plane that we computed earlier in the last video at this particular point. Now what we can do is we can say, okay, let's consider the point, say 0.1 and 1.9. You say, okay, well, what is the function value? So what is f of 0.1, 1.9? Of course, you could plug it in directly, but this is approximately equal to L of 0.1, 1.9. You say, okay, well, so this is our linear approximation. This is called a linear approximation. Of course, in this particular example, it's not super enlightening. You probably could just plug it in directly. But just for the sake of it, there are lots of practical situations where the linear approximation is all that's really available, especially when you're doing like data analysis or something. So you use this linear approximation. We'll say, okay, well, what is L of 0.1, 1.9? This is 12 minus 4 times 1.9. And so, well, what is that? Let's just punch that in. I'm just going to punch that in here into my calculator. 12 minus 4 times 1.9. So this is 12 minus 7.6. And so we get 4.4 as our answer. So this is the procedure for the linear approximation. The only real requirement is that our point here, so notice that the point 0.1, 1.9 is, I'll put this in quotes, close to the base point 0, 2. How close is close? Well, that sort of depends on the example, but usually it's within a couple of decimal places, and that's essentially the linear approximation. So we can always use the tangent plane to approximate function values near the base point. So the key thing is near the base point. The further away you go from the base point, the further away the approximation is. And this is actually, not that we're going to talk about this, but this is actually the first order Taylor approximation in multiple variables. We won't get into that, but it's an interesting point.